Hello and welcome back to CS422, Introduction to the Theory of Computing. And we are talking about advanced computability, chapter 2, and specifically Rice theorem. So let's recall what Rice theorem is about. And here we go. Rice theorem is a very strong generalization of the undecidability of the halting problem. The halting problem is one specific question about semantic properties of an algorithm. And I emphasize semantic properties because syntactical properties of an algorithm usually are decidable, and that's why we generously ignore any syntactical questions about syntactical correctness of programs, and instead we focus about semantical properties. And one semantical property is whether the given program terminates or not. That's the halting problem. And what is specific about semantical property? How can we define semantical property as opposed to syntactical property? And one way of defining a semantical property is to say that a property is a semantic property if proceeding to a different but equivalent algorithm does not change the property. Let me say it again. Suppose you have an algorithm which behaves in a certain way on some inputs, in a different way on other inputs. In our setting, algorithm usually wins a while program. And now we proceed to a different while program, but an equivalent one, in the sense of equivalence that we introduced when we talked about semantic fixed points in the fixed point theorem. So a different while program, but an equivalent one. Then syntactical properties can change when proceeding from one while program to another equivalent one. For example, the nesting depth of loops could change, so that's a syntactical property. The number of variables, the code length, these are all syntactical properties. Semantic properties, on the other hand, are defined by saying that they do not change when proceeding to a different but equivalent while program. So that's what makes semantic properties stand out compared to syntactic properties. And Rice theorem can be paraphrased saying that any non-trivial semantic property is undecidable. Okay. And as I said, this generalizes the halting problem because the halting problem is a semantic property. Proceeding from one while program to a different equivalent one, equivalent entails that it does not change, that it has the same termination behavior as the other one. So that's a semantic property. And what does it mean for a semantic property to be non-trivial? It means that the property that is always true, which is a semantic property, right? Modifying while program does not change the property which is always true. And the other trivial semantic property is the property which is always false. And these are semantic properties, and they're obviously decidable, right? There exists an algorithm which just says yes for the trivial true property, and another algorithm that always says no for the trivial no property. So these are obviously decidable. And Rice theorem says that any non-trivial semantic property is undecidable. So that's very, very strong statement. And it covers basically all the problems that occur commonly in program verification. For example, if there's some subroutine, some function, will this function ever be called? That's a semantic property. Will the program ever output something? Is a semantic property. Proceeding to a different but equivalent while program, yeah, that's the whole point. Does not change the output behavior. That's our core of the proof of the fixed point theorem. We would proceed to a different but equivalent program which has the same output behavior and all other behavior, but now knows its source code as opposed to the previous one. So these are great examples of semantic properties, and Rice theorem says these are all undecidable. So to recall, syntactical correctness is a syntactical property. It's decidable. How long a program is syntactical. How many steps does it make? At most 1,000 steps. That is also decidable, right, by simulating. And that's not a semantical property because we can proceed to a different while program which behaves in a faster way. For example, replacing a bubble sort with quick sort, or the opposite, replacing quick sort with bubble sort, changes the performance of a program while the overall behavior remains the same. So this is again not a semantical property, and this explains why it's decidable on a higher level, whereas the termination, the halting problem, that's a semantical property, and we already know that to be undecidable. And another semantical property here is the non-triviality problem. Does there exist some input on which the program does terminate? And more generally, we introduce here the notion of L of P is the set semi-decided by program P. Every program semi-decides some set, namely those inputs where the program terminates, without those inputs where the program does not terminate. And whether this set is empty or not, that's exactly the non-triviality problem that we introduced earlier when we compared problems with respect to undecidability, and we saw that this is also undecidable because, and now from this higher level perspective, because it is a semantical property and not a syntactical one. Proceeding to a different program which is equivalent still has the same, terminates on the same inputs and outputs, semi-decides the same set. And the Rice, or more generally Rice, Mahil, Shapiro theorem says the following: fix a subset of the power set of natural numbers. And imagine this is the set to be semi-decided, the collection of sets to be semi-decided by a program. And we want this to be non-trivial. That means we want at least one subset of natural numbers to belong to this hyperset, right? This collection of subsets. And we want one to not belong to that. That's the non-triviality of this collection of subsets. And for each such collection of subsets, we consider the induced decision problem, semantic decision problem on programs, namely, for given a program, is the set semi-decided by this program, right? Recall every program semi-decides a set. Is the set semi-decided by this program? Does that belong to this collection of subsets or not, right? So the set semi-decided program is a subset of natural numbers, the set of natural numbers where the program terminates. And the question whether for a given program this subset belongs to this collection of subsets or not, that's a decision problem on programs. And it is a semantical decision problem because proceeding to a different but equivalent program, yeah, by the very definition of being equivalent means the program has the same, the semi-decides the same set and therefore does not change, is invariant, that's a technical term, under proceeding to different but equivalent programs. And the Rice-Meyer-Hill-Shapiro theorem says this decision problem is undecidable, provided that the set collection is non-trivial. It contains at least one semi-decidable, important, one semi-decidable set, and it will misses at least one semi-decidable set. And yeah, so this covers, for example, the non-triviality problem, where the set here contains all non-empty subsets, for example, right? Yes, here's a great question in the chat. What is the definition of L minus and L plus? Is this just arbitrary partition of sets? That's a very good question. That's a great question, because now I have all reason to explain that in further detail, right? So the terminology, don't let yourself be confused. It basically just means that some semi-decidable set must belong to S, and some semi-decidable set must not belong to S, right? So let me explain why we impose that condition. Consider as a collection of set the empty collection, the collection that contains no set at all, right? Then this decision problem is decidable, right? Because then the set semi-decided by a program never belongs to this collection, because this is an empty collection, right? So this is, in this case, it's decidable, which means in this case, the theorem looks like wrong, but it is not wrong, because in this case, this hypothesis, these two are hypothesis is violated, namely the hypothesis that this collection of set must contain at least one semi-decidable set, right? If we choose this to be the empty collection, then this empty collection contains no semi-decidable set, and thus violates the condition. The other extreme is when this is the collection of all subsets of natural numbers. Then again, this decision problem is decidable, because if the S is the collection of all subsets of natural numbers, then whatever program P is, the set semi-decided by this program is a subset of natural numbers, and therefore belongs to the S, the collection of all subsets in the case we're currently considering, in which case this problem is trivially decidable just an algorithm which just always says yes without even considering its input. So, but this case is also prevented by the hypothesis that the set S must not contain some semi-decidable set. So this second line is a hypothesis, not a conclusion. It's a hypothesis for the theorem that formalizes the intuition that the collection of set should be a non-trivial collection, because every non-trivial semantic property is undecidable. Trivial semantic properties are decidable, but the non-trivial are undecidable. And this second line formalizes this condition, this hypothesis, that this collection of set is non-trivial by requiring that this collection of set contains at least one semi-decidable and misses at least one semi-decidable. So there's nothing about a partition here, right? So there's no mentioning of a partition or anything. These two sets, L minus and plus, they can, but they don't have to be disjoint at all. It just has to be that these two sets, L minus and L plus, must be semi-decidable. That's an important hypothesis, which we also called enumerable, remember at the beginning? So as long as this collection of sets S contains and misses a semi-decidable set, two semi-decidable sets, then the conclusion holds that then the decision problem is undecidable. Does that make sense? Right. So no partition here. And also it's not required that L minus or L plus be non-empty. They just have to be semi-decidable. Okay. So let me illustrate an application. And we know the proof that the non-triviality problem is undecidable is now a simple consequence of the Rice theorem, and thus demonstrates how extremely powerful Rice theorem is. Then we consider as S, capital S, the collection of non-empty subsets of natural numbers. So this is almost a trivial. The trivial collection is that contains all subsets. But now we remove one, we remove the empty set from the power set. And thus we arrive at a non-trivial collection of subsets, okay? And this non-trivial collection of subsets satisfies the hypothesis. It contains a semi-decidable set. It contains many semi-decidable sets. It contains many sets. It contains almost every set except for the empty set, right? Right. Remember that the confusion between the empty set and the set that consists of the empty set. The set that consists of the empty set is non-empty. And here we have the kind of opposite. Here we have the set that consists of all subsets except for the empty set. So we have many semi-decidable sets in that hyperset. And we have a semi-decidable set which does not belong to this, namely the empty set, which we've just removed. So we can now recover the undecidability of the non-triviality problem with a case where capital S is a set of all subsets of natural numbers except the empty set. And here the hypothesis is satisfied with L minus being the empty set, which is a semi-decidable set, right? Empty set is semi-decidable. It's very easy to decide, right? But it's not does not belong to the collection S, as we are currently discussing the current application. And therefore, according to Rice theorem, the non-triviality problem is undecidable, which we knew before, but now it's a simple application of the Rice theorem. So Rice theorem is very general and very powerful. That's a message to take away from here. And then we've given the proof of Rice theorem. And the proof of Rice theorem actually builds on our already known fact that the halting problem is undecidable. So it's not kind of a new proof of undecidability of a halting problem, but a generalization. Since we already know the halting problem is undecidable, we then make a very generic universal reduction from any non-trivial semantical problem, from the halting problem to any non-trivial semantical property. Okay, so that's what we do here. And here, for your convenience, I've stated again in quotes the plain language interpretation of Rice theorem. Any non-trivial semantic property of a given program is undecidable. And non-trivial means that here, and semantic means that. Okay. So in further proof, we would consider two cases. The first case is that the empty set belongs to S. Recall the empty set is a semi-decidable set. And the second case where the empty set does not belong to S, that's basically the case of the non-triviality problem, right? So if the empty set belongs to S, then we're going to devise, we prove by contradiction, we suppose that the set is decidable. And then from that, we derive an algorithm which decides the halting problem, which is a contradiction. And how do we decide the halting problem? So for the halting problem, we're given a program P, and during the reduction, we convert that program P into a program Q with the following behavior. It first simulates P, and if P doesn't terminate, then neither will Q. But if P does terminate, then after that, following that, our new program Q will invoke the program semi-deciding L minus. by the hypothesis that L minus is semi-decidable and does not belong to this collection S. Now we can easily see that the newly constructed program Q semi-decides L minus if the program P does terminate, whereas if the program P does not terminate, then the newly constructed program Q will never get to invoke the program semi-deciding L minus, and therefore will never terminate. That never terminating means semi-deciding the empty set. So to summarize, the newly constructed program Q semi-decides the empty set, never terminates. If the given program does not terminate, does not belong to the halting problem. Whereas if the given program does terminate, does belong to the halting problem, then the newly constructed program Q semi-decides L minus, which is exactly the definition of this semi-decision problem. In the first case, the subset semi-decided by the new program Q is the empty set which belongs to S. In the second case, it's a set L minus which does not belong to S. So in the first case, the answer here would be yes. And in the second case, the answer would be no. So that from the answer, one can recover and thus is able to decide the halting problem, the termination of the given program P, which is a contradiction because we know that whether program P terminates or not is undecided. That's the first case, the case where the empty set belongs to this set S, hyperset S. The second case, suppose that this empty set does not belong to S. What are we going to do then? Then we first perform, again, we make a reduction, convert the given algorithm P into a new algorithm Q, and analyze the behavior of Q. But in this case, the new algorithm Q will first perform P as before, and then proceed to invoke and simulate the algorithm that semi-decides L plus as opposed to L minus. Now again, using the hypothesis that L plus is semi-decidable and that L plus belongs to S. Whereas in the case we're currently considering, we suppose that the empty set does not belong to S. So that again, we see that if P terminates, then the new program Q semi-decides L plus, which does belong to S, and thus requires a positive answer here. Whereas if program P does not terminate, then the new program Q does not terminate either, which means the new program Q semi-decides the empty set, which does not belong to S, so that the answer here is negative. So that again, from the answer, whether the new program Q belongs to this set or not, entails the question whether the given program P terminates or not the halting problem, which is a contradiction. So that also a proof of Rice's theorem. Every non-trivial semantic property of a given program is undecidable. Okay, so that was our recap and wrap up of this part. And now we're moving on to more advanced topics in theory of computing, namely Oracle while programs, which is a counterpart to Oracle Turing machines introduced by Alan Turing in his PhD thesis. Many years after he introduced and invented the Turing machine. And following our pedagogical paradigm of avoiding Turing machines altogether and instead using while programs, we also avoid Oracle Turing machines and instead consider and introduce Oracle while programs. So what is an Oracle while program? An Oracle while program is a while program as we know it, but with a newly introduced instruction, assign to variable xj the value of a function phi on the given value of another variable. So once the program has calculated some value in the variable xi, then it can invoke that new instruction, which produces a new natural number, because phi is a fixed total function, not necessarily computable. That's the point. Here we do not suppose that phi is computable. If phi is computable, then one can replace this new red instruction with a program, while program that computes phi, and thus can kind of replace all occurrences of this red instruction with actual classical while programs. But if phi is not computable, then this new instruction cannot be replaced by our classical while program, and thus makes Oracle while programs strictly more powerful. For example, suppose that phi is the characteristic function of the holding problem. Right? Remember, characteristic function has only values 0, 1. 1 in this case if the argument belongs to the halting problem, 0 if it does not belong to the halting problem. So in this example, when phi is the characteristic function of the halting problem, adding this new instruction, proceeding from classical while programs to Oracle while programs, strictly increases the power, because now using that characteristic function of the halting problem, the Oracle while program can decide the halting problem, right? Okay, so fix some arbitrary total, not necessarily computable function from natural numbers to natural numbers, and kind of imagine that as a black box subroutine that returns a value, okay? Or it's like a black box function in your favorite programming language, except this function is now so black box, it doesn't even have to have an algorithm behind it, implemented. It has to be well specified. Okay. So here's some examples of such functions to add to the while program. For example, the characteristic function of the primality problem. Primality means given a natural number, is it a prime number or not? So the characteristic function of prime numbers, the primality problem, is 0 for 1 and 4 and 6 and 8 and 9 and 10, whereas it is 1 for the prime numbers 2, 3, 5, 7, 11, 13, and so on. So primality problem, decision problem, but now converted into a function problem, and namely a characteristic function. Here's another example of such an Oracle function, gain a characteristic function, the function of the halting problem, as we've just discussed, allows an Oracle while program to decide the halting problem basically by simply invoking this characteristic function Oracle. Or we can consider the characteristic function of the totality problem, which, as you recall, is strictly more undecidable than the halting problem. So by adding this characteristic function to the while programming language as an Oracle, one can now even decide the totality problem again by simply invoking that function. And one can decide the halting problem because the totality problem is strictly more undecidable. Also observe that now we do have a closure under composition, under complement. Of course, we can kind of always, after invoking this Oracle, have an additional instruction that simply flips the outcome of the Oracle, flips the return value bit if it's a characteristic function. But in general, it can be even more. Could, for example, be the integer factorization problem, which is not a decision problem, as you recall, but a function problem. Return some non-trivial factor of a given integer. Primality as a decision problem is known to belong to be polynomial time decidable. We're going to talk about polynomial complexity in the second path. But factoring is not known to be possible in polynomial time. So we can capture that here in this setting with a function Oracle. And yes, we've previously talked about reduction between decision problems, right? L and L prime, or decision problems, that is subset of natural numbers, meaning those elements that belong to L correspond to an answer yes, and those that do not belong to L correspond to the answer no, decision problems. And we've talked about the notion of reduction between such decision problems. And now we are in the position to generalize that from decision problems and reduction to function problems and reduction between function problems, which is what we're going to do now. So for two function problems, psi and phi, we say that psi is reducible to phi if there exists a while program with oracle. That's why we introduced oracles. With oracle phi, function oracle, that is able to compute psi, so an input x, output psi of x, using possibly the one or several calls, so this oracle phi, with pre or post processing or intermediate processing. Anything is possible and allowed. So this is our new notion of reduction between function as opposed to decision problems. And I want to ask you to verify that this new notion of reduction first generalizes the previous one in terms of a characteristic function. And secondly, it satisfies the same properties, and in particular, it satisfies transitivity. So one property that I'd like you to verify is that if the phi is computable, then so is psi under this reduction, which you recall makes sense if we recall the meaning, the intuition behind the simple meaning. Psi should be at most as difficult as phi. So if phi is already computable, then we expect that also psi is computable. Cannot be harder by the intuition, and you're asked to prove that, which is kind of trivial. So please do that, not now, but at the end of today's lecture in a quiz. So the second property that I'd like you to verify, which is also right, observe that this also generalizes the decidability of the decision problems to function problems, right? And same for the second property, the transitivity of this notion of reduction between function problems. Again, something I'd like you to think about and do at the quiz at the end of today's lecture, not now, please. Okay, so the baseline for now is what I want you to remember here in the sequel is that this is a generalization of the notion of reduction that we already had for decision problems to function problems, and that it satisfies all the good structural properties of reduction, again, that make it a reasonable notion, and in particular, it's a partial order, except for anti-symmetry. And now we can rephrase what we already know about comparing the degrees of undecidability of the decision problems. Primality problem is decidable, halting problem is undecidable, totality problem is even more undecidable. We can now rephrase that in terms of comparing them as function problems using the characteristic function. But one important subtlety is now, as I said, we do have close undercomposition, meaning that although as decision problems, the halting problem and its complement were different, one is semi-decidable, the other is not. But as function problems, as total function problems, that's important, they are actually equivalent. Think about that. And why have we introduced this new Oracle while programs? Because now we can study from a better perspective this hierarchy of more and more undecidable problems. I promised you that on the bottom are the decidable problems. Then there's undecidable halting problem and non-triviality problem. Then there's even more undecidable totality problem. And I've promised you that this goes far up. And here we are going to see that. And to do that, we introduce some notation. Namely, we formalize the lowest class of this hierarchy that we're now going to introduce and construct. The lowest level consists of all decidable problems, all decidable subsets of natural numbers. And for this, we introduce three notions: delta 1, sigma 0, and pi 0. And this seems a little bit confusing. Also, why is there 1 here and here, 0 here and here? And trust me, this will become clear very soon and also start to make sense soon. For now, this is kind of, imagine this is kind of the induction step, which if you look at the induction step of any proof, the induction start of any proof doesn't usually make any sense unless you already know the proof or the statement. The induction start by itself is often confusing, and the same is here. So please stay tuned and follow up with me when we now paint this picture further. So now it really justifies delta 1 as a lowest level of the hierarchy we're currently constructing and building. And what we do now is we kind of climb up by saying next level is the previous level being available for Oracle access in order to define the next level. So it's kind of an inductive definition, which you see here. Delta k plus 1 is defined to be those decision problems, subsets of natural numbers, that are decidable provided they have Oracle access to some problem in sigma k, where sigma k is in turn going to be defined inductively. We already have defined sigma 0, and we have defined sigma delta 1. And if you look at this, let's plug in k equal to 0 here. Then that means decidable with Oracle access to something decidable, right? Sigma 0 when k is equal to 0. Decidable by a while program with Oracle access to something decidable. Remember, any decidable Oracle can be replaced by an actual while program without needing any Oracle access, and therefore doesn't increase the power, and therefore this is still only decidable. So it's still delta 0 plus 1. So that means this definition is consistent with the induction start that we already have. And same here for pi 0, decidable with Oracle access to pi 0, but pi 0 is the same as sigma 1. So this is this inductive step definition is consistent with the induction start definition with case k equal to 0. But we also need inductive definitions for sigma k plus 1 and for pi k plus 1, right? So we only have now defined inductively delta k plus 1 by induction on sigma k or pi k, but we haven't defined inductively pi k yet. So let's do that. But first already paint a picture how these are going to be located and form a hierarchy, which will be justified in a few minutes. And the first property of this delta family of decision problems is the following, that not the family is closed under composition. That's a common source of confusion and mistake. So this is the set of all complements of subsets in this here. So this is not the complement of this set, but it's a set of complements of sets in here. Does it make sense? And the statement says that this is still the same set, which is a generalization of what we already knew in the very early slide, that any decidable problem also has its complement decidable. And this is now true also on higher levels. Any problem here also has its complement here, not necessarily decidable, but again here, any problem here also has its complement again here, and so on. That's the delta classes. But here we have two more classes, and you will see in a minute why they're really important, and we need to introduce them for the induction step. And here's the induction step for sigma k plus 1. This is defined to be those subset of natural numbers that are semi-decidable by a while program with Oracle access to any decision problem here in sigma k. That gives rise to sigma k plus 1. That is the induction step. And what does it mean here to be semi-decidable with respect to some? That means we fix some characteristic problem of some decision problem in here, any, and then we can take the first one and give rise to this inductive definition. And the other hand, kind of mirrored, is the inductive definition of pi k plus 1. This is those problems that are co-semi-decidable. That is the complement of a problem that is semi-decidable, again with Oracle access to the sigma k. Okay, so and one question that I hope you're raising is, why is it in both cases sigma k? Wouldn't you expect here pi k as opposed to sigma k? Who is asking that question? Nobody? Yeah, that's I mean, just out of, we're defining something here. I can define anything I like, right? But it is reasonable. Is it reasonable to define this in this way and this also in this way without referring to pi k? And the answer is yes, because it doesn't matter. Because as we'll see and prove by induction and already see here, this is the complements of the sets that are semi-decidable, the complements of the sets here. And now recall that the oracles are closed under composition. So if we have some set here as such an oracle, then we can also have its complement as oracle and recover the original one by flipping the return value. So it makes no difference in terms of oracle whether we use pi k here or sigma k here or pi k here or sigma k here. So that's the answer to the question. And the second statement of the lemma, which is now also going to be easy to prove by induction, is that delta k, as thus defined inductively, is actually the intersection of sigma k and pi k, as thus defined inductively here. Again, this is something we knew. So let's, for example, consider the case sigma 1. What is sigma 1? Sigma 1 is when k is equal to 0, right? Sigma 1 is the set of problems which are semi-decidable with oracle access to sigma 0. Now recall, what is sigma 0? These are the decidable problems. Giving oracle access to decidable problems does not give more power. It can be replaced equivalently, semantically equivalently, with an actual program deciding it, and thus this oracle, any sigma 0, any decidable oracle, can be kind of removed from oracle programs, and thus obtain an equivalent, semantically equivalent oracle-free while program, so that being semi-decidable with oracle access to sigma 0, decidable, is the same as just being semi-decidable, so that sigma 1 is a set of semi-decidable problems. Okay. Now let's look at pi 1. Pi 1 is the complement, the set of complements of semi-decidable problems. Again, it doesn't matter whether we have oracle access or not, because the oracle is from sigma 0, and sigma 0 is decidable, and thus can be kind of replaced, the oracle, by an actual algorithm that does not use an oracle. So it's basically the complements of semi-decidable problems. That's pi 1. And what is delta 1? Well, we already know delta 1. We've seen that this is consistent with that. But what is delta 2? Delta 2 now means it's a problem that are decidable with oracle access to sigma 1 or oracle access to pi 1, right? Recall that this is the same in Hahn. We see why it's the same, because sigma 1 is a semi-decidable, so something being decidable with oracle access to semi-decidable, or decidable with oracle access to co-semi-decidable. That's delta 2 here. Okay. But below delta 2, according to this here, are these two classes, the delta and pi classes. And item B and C of the lemma say that they're indeed between, and strictly between, and the intersection of both is the delta class. So here's a picture. So we have delta 1, decidable, right? And we have sigma 1, which we call this semi-decidable, which is more like the halting problem is semi-decidable but not decidable. And we have pi 1, which is a complement of semi-decidable. So, for example, the complement of the halting problem is here, but not here, not to mention here. And moving up further, the union between those two classes, any problem that is either semi-decidable or its complement is semi-decidable or both, that's strictly more than just being semi-decidable, as for example, the halting problem illustrates. Whereas this here is the intersection. This is the union, either or, and this is the intersection being both. What? Being both in, according to this theorem, this lemma, in sigma 2 and in delta 2. So here you see sigma 2, and here you see pi 2, not delta 2, pi 2, and the intersection between two classes, the decision problems that belong to both, these are precisely those in delta 2, and so on. And you can see how we can climb up that hierarchy, defining to be semi-decidable, decidable, or co-semi-decidable with an oracle that belongs to the lower level, previous level, gives rise to strictly increased power. Well, I haven't proved that it's strictly increased, but we'll do that in a minute. So that's one way of introducing what is called the arithmetic hierarchy. Okay, inductive introduction, and here's the property. There's also semantic, no, that's a semantic. There's also syntactic characterization that, but we'll leave that to maybe later in terms of quantifiers, universal and alternating quantifiers. So what I'd like you to take home from here, from this previous two slides, is oracle while programs, and using these oracle while programs in order to define inductively the levels of the arithmetic hierarchy corresponding to more and more undecidable problems. And for example, the totality problem. Totality problem is a problem that belongs into this class. It is in this class and it is maximal. It's not in any lower class, totality problem. Whereas the halting problem is in this class and maximal here, maximal in this class. And the non-triviality problem is also here in this class. And the complement of the non-triviality problem is here. Okay. So that's a arithmetic hierarchy. And as a next and arguably most advanced topic of chapter 2, computability theory, is post problem. So let me first motivate post problem. We've just seen with the hierarchy more and more undecidable problems. So for example, the non-triviality problem and halting problem are both equivalent, and they can be decided by while program P given Oracle access to the non-triviality or the halting problem, which is the same. Whereas the totality problem is strictly more undecidable. It's on a next level. And one can show and see that this is the same as the halting problem with Oracle access to the halting problem. So that's a very subtle notion. That means the halting problem for while programs is where the given while program terminates. Now, if we consider Oracle while program, that's a question whether given while program having access to the halting Oracle terminates. And that turns out to be even more undecidable. Right? So even access to the halting problem cannot tell whether a given while program that also has access to the halting problem terminates. And this is the next level. And one can iterate that and produce higher and higher undecidable problems, h to the h to the h and so on. And but Emil Post, this has been known long, this hierarchy goes on infinitely high. It never encompasses everything, but it keeps going on. And Emil Post asks, actually on the lower level, is there anything between the undecidable halting problem and the even more undecidable totality problem, which is equivalent to the halting problem for while programs with halting Oracle? Is there something in between, something strictly in between? That was Emil Post's first question. And his second question is, are there problems that are incomparable? Well, so far, we've only considered problems that are strictly more undecidable, like totality, or that are equivalent, like non-triviality. Is there something in between that is strictly more undecidable than halting problem, but strictly less undecidable than the totality problem? Is there something like this? This was Emil Post's second question, 1944. And these questions both turned out to be very, very difficult questions. And people try to disprove the answers and fail. And then they try to prove that the answer is positive and failed, until two very smart logicians actually found a new way of constructing undecidable and conducting undecidability proofs. So let me first rephrase the second question. Do there exist semi-decidable problems such that the first one is not decidable even when given Oracle access to the second? That means it is strictly more undecidable. Nor is the second one decidable with Oracle. The first means that the second one is also strictly more undecidable, which means the two problems are incomparable. So Post's question from this abstract level was about the degree structure using the notion of reduction we've just introduced, partial order. Is this a first question of a second question of Post basically says, is it a total order? Means, can any two problems be compared? That's what makes a total order, or not? So that's a very natural question to ask about the structure of computability and uncomputability to anyone who has learned about partial orders like you have in discrete mathematics. Is a partial order actually a total order, a linear order or not? And that's Emil Post's second question. And his first question is whether this order is actually a discrete order, whether it necessarily proceeds in these jumps, halting problem, totality problem that we've experienced, or whether it's something in between. And it turned out that the answer to both is yes, very surprisingly, but it took more than 10 years and it took very smart people to assert that, to find that answer. First person was Friedberg from the United States, and the other person, Muchnik, from Soviet Union, it was called at that time. And they both provided an answer independently because, you know, at that time it was the Iron Curtain, so that scientific exchange was very difficult and very limited. So none of each knew of the other. Okay. And only later became apparent that both actually had solved Post's problem independently. That's what I'd like to emphasize here, independently. That happens. Okay. So now recall, I want to make this statement of Friedberg and Muchnik's answer to Post's problem more transparent. And so recall our new notion of reduction between function problems using Oracle-wide programs. And so Post, actually he conjectured that this induces a total order on problems, and furthermore that it is a discrete order, step by step. So this is the terminology that has been introduced then. This is a symbol for the decidable problem. So this is now in boldface, meaning this is a class of problem, a hyperset. This is all semi-decidable problems. This is so all problems in sigma 1. These are all problems in sigma 2, sigma 3, and so on. And the notion sigma 1, 2, 3 suggests that there should be a total order, right? So sigma 15 is strictly larger than sigma 12, and there's no sigma 13 and a half floor. But that only applies to the arithmetic hierarchy, whereas other problems turn out violate or lie outside of this. And so that's what we indicate here. So here you see also decidable. And what Friedberg and Muchnik did, they both independently actually constructed two problems that answer both Post's question at the same time. First, two problems that are incomparable. So B is not reducible to C, nor is C reducible to B. But, and from that it immediately follows that this is something that lies strictly between the decidable and the halting problem. So that's Friedberg and Muchnik's result. And the proof is very sophisticated, very smart, and they had to introduce a new technique, which is called the finite injury priority technique, in order to construct something, in order to show that something exists. And as I keep emphasizing, to show that something exists, which does not exist, that's really the key difference between science and engineering. I'm not saying that the problems constructed by Friedberg and Muchnik have practical relevance or lack practical relevance, but they did prove that such problems exist, and thus open up the further investigation whether and to what extent these problems are have practical relevance. Otherwise, yeah, actually Post's original conjecture was that such problems do not exist, but he failed to prove that. Okay, so that showing that they exist is a proof of impossibility proof to prove that they do not exist, which was what Post tried to do. Anyway, so let's talk about this new advanced method of constructing using diagonalization, which is a generalization of the construction of diagonalization that we already learned long ago at the very first lecture, where we talked about the halting problem. And remember, the purpose of diagonalization is to as a technique in an indirect proof in order to raise a contradiction. First, suppose that the halting problem is decidable, and then we took the hypothetical algorithm that decides that and converted that into something that would do something by flipping the output of the given algorithm, of the hypothetical algorithm. That's the diagonalization. And then would result obtain something that cannot be true, this contradiction. And so I'm going to review that and generalize that technique here. But first, let me now make a formal statement of what Friedberg and Mucknick proved. They proved that they exist undecidable, but semi-decidable. So meaning they're below and strictly below the halting problem, which is undecidable and semi-decidable problems called A and B, subsets of natural numbers, such that A remains undecidable even if given B as oracle, although B is itself undecidable, and vice versa, which means both the two problems cannot be compared with respect to their degree of uncomputability, and they are both strictly easier than the halting problem, yet undecidable. Okay. And from that it follows, if that has been proven, or this is basically equivalent to saying that the complement A is not semi-decidable with oracle B. Right? Remember, we proved that set is decidable if and only if the set is semi-decidable and its complement is also semi-decidable. Since these two sets A and B are supposed, or by hypothesis, are semi-decidable, saying that they are undecidable means that their complement are not semi-decidable, and being undecidable with oracle means that also their complements are not semi-decidable with oracle for the first set A, and vice versa, meaning the same is true for the complement of the set B, not semi-decidable even with oracle A. And we're actually going to construct such sets. Okay. And as a warm-up, let's recall some standard diagonalization. This is sometimes called the diagonal problem. The diagonal problem is another semantic property of program. Does the program terminate on its own, not terminate on its own input? In the not, this is what makes the diagonalization. This is kind of how to fool any possible candidate program. So if this were decidable, then we could investigate what would the algorithm that decides that problem, does it terminate on its own input? And we would see that it does not, nor does it. So it's a paradox. And generalization is now to construct these semi-decidable sets with the following property: to any program there exists an input such that this input belongs to the first problem if and only if the program with the second problem as oracle on input X terminates. Let me say it again. So to every program there exists an input X to that program, a natural number, which depends on that program. So for a different program, it would be a different one, such that either both are true or none of these are true. That's what equivalence means. Both meaning true means X belongs to the first decision problem A and the algorithm P we're considering, while program P we're considering, with Oracle access to B, the second problem we're still need also to talk about, on input X terminates. Let me spend a minute to expand on that terminology. And recall this or notion that means Oracle access to the decision problem B, or more precisely to the characteristic function of this decision problem. And that here means on input X. So this is an Oracle while program, and consider a thought experiment running that on input X, and it may terminate or may not, right? We don't know, but if it terminates, then this X must also belong to A and vice versa. That's what we want to show. We want to construct such an X for each P, and dually or similarly for the other. For every program, while program Q, there exists an input Y that depends on Q, such that either both Y belongs to B and this while program with Oracle access to I on input Y terminates, or none of those. Y does not belong to B, and this algorithm Oracle while program with Oracle access to A on input Y does not terminate. Why is that a good proof strategy to show that? Because then one immediately arrives at Friedberg and Muchnick's result and statement, right? Maybe if this is true, then let's suppose that there exists a program which does semi-decide this complement with Oracle B. Okay, suppose we have proven that. And now to conclude the theorem by contradiction, suppose that there exists an algorithm that does semi-decide this with Oracle B. Then let's consider what this algorithm does on the, let's call that algorithm P, while program P, and let's consider what this while program P does on input X with X as indicated here. This while program P on input X, well, by the very definition, if X belongs to A, so it does not belong to the complement, then the algorithm terminates, which means it semi-decides which such a way that this does belong to the right, because termination means it semi-decides this complement, but we've just considered an X which does not belong to the complement, but it belongs to A. And similarly, if this X does not belong to A, then that means that this algorithm while program with Oracle B on input X does not terminate, which means again gives rise to contradiction. Yeah, I'm talking too much and thus more inhibiting your thought. Please figure out yourself that once we've established these two statements, then it immediately follows these two statements. Immediate proof by contradiction, generalization of the proof of undecidability of the halting problem. And these two statements indeed are the same as Friedberg and Muchnick's statement. So, oh, here's a great question in the chat. What's the difference between P and P with exponent B? Exactly, good question. It means this is a while program P. So P is always a program, and in our class it means a while program, and Q is also a while program. And this is a while program, an Oracle while program. Remember, we introduced Oracle while programs a few slides before, where the Oracle is now not some function, but the characteristic function of P, where P is a decision problem we're talking about. And similar here, this is an Oracle while program with Oracle access to the characteristic function of a decision problem A. Okay, so let me revert a little bit back to when we talked about Oracle while problems. Right here, that's Oracle while programs. Okay, and we've introduced or considered example characteristic function as oracles. So when we talk about here it's sitting right. So when we talk about P to phi the exponent, it means phi is oracle. Yes, and that means P on input X, the program P on input X, and the program P with exponent Y on input X can be different. Actually, the program P could be, cannot even make an Oracle query, cannot even invoke that function. And imagine in your favorite programming language that phi is some external library function that somebody else is providing to you without telling you how he or she has implemented that, and possibly even using some miracle, some undecidable or uncomputable function like busy beaver function, for example. Okay. Yes, thank you. Great question. If you have another question, I'm more than happy to expand on that, because, yeah, frankly, I'm well aware that this is very advanced, but my promise is this is here we are. This is as advanced as it gets in chapter 2. Remember, each chapter we try to deliberately start very slowly and then gradually ramp up the difficulty. And we're almost at the end of chapter 2, and thus this is almost the highest level of difficulty. The highest level of difficulty, frankly, will be next Tuesday, when we give the proof of these two statements, where we construct these two sets in a very smart and intertwined way, because they depend on each other. So that's all for today. Yeah, I'm going to recall the statement and this advanced diagonalization at the beginning of next Tuesday. Thanks for your attention, and see you next time.